Good evening, everyone. My name is Mr. Chu. Welcome to O-Level Physics lesson. Today is Tuesday, 30th August. And we'll be doing questions on electromagnetic induction. Okay, last week I did not cover one important part about electromagnetic induction. So let me go through that with you with a question. Okay, so let me explain this question to you. Okay, let me explain this question to you, and then okay, so let me explain this question to you. Let me start the thing. Okay, so last week we mentioned about what will happen down here. Okay, what happened down here when when there is a change in magnetic flux cutting through the solenoid. So this example we did not go through last week. Okay, we did not go through last week. So let me go through this question with you all. Those who can answer the question can give me the answer. Okay, if not, just listen to me. Okay, so this is a vertical coil. Okay, it's connected. There's no battery, there's no other thing, but it's connected to a sensitive ammeter. So if there's any current in the whole circuit, the ammeter will move. Is that clear? So as a magnet force through the coil, the ammeter needle move quickly to the right. Okay, so as you go down, it will fall quickly to the right. So the magnet will fall through the coil. So how does the ammeter needle move as the magnet falls away from the coil? So how does it move when it moves away from the coil? Anybody would like to try this? Okay, so only Pei Kwan gave me the answer, and answer is correct. Okay, so before we continue, okay, let me revise Lenz's law to all of you. Okay, let me revise Lenz's law to all of you. Okay, all of you look at this. Okay, last week I did not mention this much. Okay, because there's no example here. Okay, so the direction of the induced EMF and the induced current will always be opposing the motion or change that produce it. Okay, this is Lenz's law. So what is this? I may explain to you in a while. So when a magnet is pushed into a solenoid, okay, so there will be an induced current because there's a change in the magnetic flux cutting the coil. So when a magnet is pushed into the right side of the solenoid with the north pole first, okay, so what does this mean? Last week I did not mention this properly. So let me just draw a coil like this, okay? If I have a magnet pushed into the right side of the solenoid, so this magnet north is here and then it's moving in. Okay, so as it's moving in, the pole down here will actually be trying to oppose this. It's coming in, it's trying to oppose the magnet coming in. So for it to try to oppose the magnet coming in, what must be the pole here? To oppose coming in, okay, if it's not opposing, it should be attracting. So opposing is repelling. So in this example, it need to be the north pole here as well. Is that clear? So as the magnet with the north pole is going into the solenoid, this part of the solenoid will be north. And then you use, when you use north, you use your right hand rule, okay, where you use your right thumb pointing to the direction of the north, and your finger, okay, your finger will be the direction of the current. You'll be able to know the direction of the induced current. Is that clear? Now, what if this north pole is moving away? Okay, what if this north pole is moving away? How are you going to oppose it moving away? So when it's moving away, is something like repel. So to oppose the repulsion, it is it is attraction. Okay, so the right side. Okay, so the right side of the solenoid will become a south pole. Okay, same thing. Your thumb points to the north pole. Your finger will be the direction of current. Is that clear? So you're clear about this? I did not mention this last week. Okay, because there's no example here. So I try to explain this today. Okay, so down here, when a magnet is pushed into the solenoid, okay, they push into it. You are pushing into it is like attraction. So what will oppose the attraction is repulsion. So for it to repel, it should be the like pole. Then when the magnet leaves the solenoid, when it leaves the solenoid, leaving is like going away from each other. It's like repelling. So what's the opposite of repelling? It's attraction. Okay, so when it's moving away like this, the opposite reaction will be to attract. So to attract, it will become unlike pole. Are you all clear about this? Okay, if you understand this, give me a yes reaction. Okay, because last week I did not mention this at all. Okay, I did not mention this at all. Okay, so let's go through the same question again. Okay, so when this magnet trying to go down at first, is trying to when it's going down, it's like attraction, right? So you're trying to oppose the attraction, it need to repel. So you need to have a unlike pole. So you'll be a north pole down here. Okay, however, so when it's a north pole down here, okay, when it's a north pole, north-south pole, the ammeter points to the right. Okay, when it's north-south pole, it turns to the right. Now, what happens after it exits? Let me draw the thing. So when I exit, this will be the north. So this will be the south, this will be north, is going down. Okay, so as it's going down, it's trying to repel. So to oppose the repulsion, you need to attract. Okay, to attract, okay, you need to have unlike pole. So in this case, to attract, the north will be below and the south will be on top. So when the north is on top, it will reflect to the right. So now the north is below, it will reflect to where? Okay, you move to the left. Okay, so the right will be both wrong. The right is wrong. The right is wrong. So it will move to the left. Okay, the thing is this, as it moves further and further away, will it maintain at the same point? Or will it just reflect to the left and then you go back to zero? Okay, so it will go to the left quickly. As it moves further and further away, you'll go back to zero. Okay, so for this question, the answer is C. Is that clear? Do you all know why it goes to the left? Okay, so everybody clear your reaction? Clear your reaction? Everyone? If you understand this question perfectly well, give me a clap. If you don't understand at all, want me to explain again, give me a no reaction. Xiaoxing, are you there? Can you hear me, Xiaoxing? Okay. So now everybody, can you give me the answer for question 38? Every one of you, give me your answer for question 38. Everyone. Thank you, Oscar. Thank you, Yiting. Thank you, Hao Rui. Bei Kwan, Ryan, and Xiaoxing, what's your answer for this question? Okay, very good. Okay, so this I did not cover at all last week. I apologize for it, but I hope that today when I explain this, you all understand very well. Okay, so we'll go through a few questions using the same concept, okay, to see whether you understand this perfectly. Okay, let's go to the next question. Okay, let's do question number 39. Okay, let's do 39. All of you, you all may begin. Let's do question number 39. Okay, Xiao Xing, well done. Yu Ting, well done. Ryan, please try again. Okay, Ryan, totally wrong. Bei Kwan, incorrect. Okay, let's say the coil, the number of coil from the primary to the secondary is in a ratio of 1:2. Okay, can you see down here? There are less coil here, there's more coil here. So this is 1:2. Okay, so from primary to secondary, there is more coil here. So we call this a step up. Okay, we are stepping up. So what are we stepping up? Are we stepping up the voltage or the current? Can all of you tell me? When we step up, we are stepping up the voltage or the current. Everybody tell me. Okay, Bei Kwan, well done. Yu Ting, well done. How about the rest of you? Okay, so from primary to secondary is 1:2, so we are stepping up. So what are we stepping up? Is it the voltage or the current? Okay, Howry, well done. Okay, so what are we going to step up down here? We are stepping up the voltage. Very good. Okay, so when the voltage go up, so the voltage itself is, okay, the voltage is also 1:2. There'll be a higher voltage on the secondary coil. So, assuming there is no loss, okay, assuming there's no loss, the power on both sides will be the same. Okay, the power on both sides will be the same. Power is the same as IV or VI, depends on, yeah, either one is okay. So if the voltage go up on the second one, the current will actually come down because current and voltage are indirectly proportional. Is that clear? Okay. Can you see this relationship? P is equal to VI or IV. Okay, so as the voltage go up, current will come down. So these two, the relationship of V and I are inversely proportional. Meaning, if I were to draw a VI graph or IV graph, it will look like this. Is that clear? With a high voltage, you have a low current. You have a low voltage, you have a high current. Can you see from this graph? Are you able to see? You have a high voltage, you get a low current. You have a low voltage, you get a high current. And when you multiply them together, you get the same power. So that's assuming that there's no power loss. When your voltage go up, your current will come down. Okay, so for B, it is wrong. Okay, B will be incorrect because the current in the secondary coil will be lower. Is that clear? Okay, then number two. Number two, you look at answer C. Some of you gave me the answer C. Anybody? Yes, Ryan and no, nobody gave me answer C, sorry. Okay, answer C is also wrong because what's happening here? What happening to the core is this. this coil of wire makes the core magnetize. So when this core magnetize, you magnetize the whole core here, and this magnetism of the core will make the coil to have an induced EMF that result in an induced current. Do you need me to explain again? Okay, I repeat. If you have a coil here, if this coil with a current flowing through it will induce this iron core to be magnetized. It's like electromagnet. Okay, it's like electromagnet. So do you remember electromagnetism? When you have a solenoid with an iron core in between, the iron core will become magnetized. But in this case, we learn about AC current. So the magnetism will go up, go down, and then reverse in the direction based on a certain frequency. Depends on the frequency of the current. Then, what happened down here? Because it's AC current goes up and down, up and down, up and down. As the current go up and down, the magnetism of this core will also go up and down, up and down. And this changing magnetism that cuts through the secondary coil will actually induce an EMF in the coil that actually induce a current in the secondary coil. Is that clear? So when there is more coil, the voltage go up. Yeah, but because you cannot create energy or power from nothing, let's assume there's no loss. As the voltage go up, your current will come down, so your power remains the same. But in real life, you will not be 100% efficient. There'll be some loss. Okay, there'll be some loss. Okay, but this is how a transformer is done. Okay, so there is no current flowing from the primary coil all the way to the secondary coil. There's no current flowing. So C is actually wrong as well. Is that clear? Okay, so a transformer are more efficient than using DC current. Okay, this is also not correct. A transformer is not used to transfer voltage or a current over a long distance. Okay, it's just the purpose of a transformer is just to step up or step down the voltage. That's all. Is that clear? Okay, so the correct answer for this is A. A is the correct answer. Why? Okay, because the alternating current in the primary coil will generate a changing magnetic field on the left side. As well, and this changing magnetic field on the left side will also result in a change in the flux linkage on the secondary side. So there's a change in the flux linkage and induced EMF will be formed. Okay, and therefore induced current will be formed. Okay, if you understand this perfectly well now, give me a yes reaction. If you are still not clear, give me a no reaction. Okay, thank you so much. Okay, let's go on to the next question. Okay, let's look at, sorry, another paper. Let's look at question number 37. Okay, so this one is the basic thing. So now all of you have learned the first question. So can all of you try question number 37 now? Can you type 37, then the answer? Bei Kwan, try again. Chelsea, well done. Oscar, well done. Yiting, well done. How about the rest of you? Okay, Bacon incorrect. Okay, Ryan. Ryan, hooray. What's your answer? Okay, everybody clear a reaction for now. Ryan and hooray. I'm waiting for you. Ryan and hooray. Okay, Ryan, incorrect. Hooray, how about you? What's your answer for this? Okay, before okay, let me go through this. So it seems like you all still do not understand this. Okay, so when this magnet is trying to push into this solenoid, okay, it's moving into it. So would attraction between these two or repulsion between these two would oppose the magnet going into it? Can you tell me? Attraction or repulsion? All of you. Yeah, repeat. This magnet is trying to go into the solenoid. So what is the opposing force? Is it attraction or repulsion? Okay, Bacon, well done. Yiting, well done. Ryan, well done. How about the rest of you? Howry, are you there? Bacon, are you there? Howry, well done. Bacon, when you try to move this into the solenoid and you want to oppose this motion, so do you want these two to attract or repel? Okay, so number one, you need to repel. Okay, number two, can you tell me next thing? To repel, because it's going in, it's trying to attract, right? But to oppose this coming together, you need to repel. So repel is like pole or unlike pole. Can you tell me? To repel, you must have like pole or unlike pole. Well done, Yiting. Everybody, are you all with me? To repel, you need to have like pole or unlike pole. Yiting, well done. Howry, well done. Hello, is like or unlike? Bacon, your answer now is correct. Oscar, well done. Okay, so to repel, you need it to be a like pole. Okay, so for it to go to the right, your Q need to be north and your P need to be south. Are you clear about that? You need this to be north. Okay, so for it to deflect to the right, your Q here need to be the north pole. Is that clear? Okay, so now you have established this. If you want to have the same direction, you need this to be north and south. Okay, so we look through these four answers. Which of these four answers will result in the Q to be an induced north pole and the P to be an induced south pole? Okay, so let me go through a few answers that y'all gave me. So let me go through. Okay, Ryan told me B. When you pull out the south pole out of NP, let me see. Okay, you pull out the south pole out of NP. It's something like this, right? All right. Okay, let me change color. If we talk about answer B, okay, answer B, you're pulling the south pole out of NP. Okay, so you're pulling away. So this is North Pole. It is North Pole. Okay, so you are trying to pull away. What's the opposing force of pulling away? Okay, wait, Okay, did I draw this correctly? The South Pole should be left side or right side? Can you tell me which is the correct one? Because I read the question, I also blur. Okay, never mind. We ignore A and B first. We do C and D. Okay, we push the North Pole in. Okay, we do C first. We push the North Pole into P. Okay, we push the North Pole into P. To oppose the pushing, you need to repel. To repel, you need to have like pole. So P will be north. Okay, so therefore this is wrong. Are you clear about this? Are you clear about this? Next, I change the color. We do D. When we push a south pole into P, okay, same thing, we need to repel. To repel, you need the light pole. So P will be south. So south will be correct. So D is correct. Is that clear? Okay, let's do A. I'm starting to get confused already. Let's do A. Okay, if we pull the north pole out of Q, this is Q. We pull the north pole out of Q. Okay, to oppose the pulling away, you need to attract. Okay, you need to attract. So to attract, you need to have unlike pole. Okay, the unlike pole. So Q will be south. Okay, so wrong. Clear so far? Now we pull the last one. I run out of color. I use red color. So for B, I'm trying to pull the south pole out of P. So we're trying to pull away, the opposing force is attract. To attract, you need to have unlike pole. So if this is south, this will be north. So north is something that you don't want because you want south. So therefore, in this question, the answer will be D. Okay, are you all clear about this, everybody? Are you all clear why the answer is D? Okay, everybody clear your reaction? Let's do the next question. Okay, so sorry. This is the part that I did not cover last week. So I hope that today you all are very clear about this now. Okay, it takes time to understand, but it shouldn't be that hard to understand the concept. Let's do question number 38. Okay, all of you try this question now. Ethane, well done. How many of you is confused? Type help in this type help if you need help. Bei Guan, well done. Hey, Oscar, well done. Auri, well done. How about the rest of you? Bei Guan, how come you appear and disappear? Xiao Xing, well done. Ryan, are you there? Okay, so this question, the what we learned before, for this simple production of electricity, is just magnet going in or going out. Okay, going in and going out of a coil. Okay, it will produce a current. That's all that we learned so far. Okay, so for this our question, okay, the answer will be just B. There's no need to add a battery inside. There's no need to add any other things inside. Is that clear? So for this our question, to induce a current in a coil, you just need to make sure that there's a changing magnetic field cutting through the coil. Okay, that's the basis of how current is produced. Okay, that's the opposite of how a current produce a magnetic field. Okay, just that for magnetic field to produce a current, the magnetic field need to be changing. Whereas for a current to produce a magnetic field, there is no need for the current to change. Are you all clear about this? So do you all see you understand the difference? So for example, if I got this wire, okay, the current is moving upwards. So if there is any current moving, the charges are moving, you will produce, okay, you'll produce a magnetic field. Okay, you'll produce a magnetic field. Is that clear? Okay, how does it work? Let me show you. Let me revise. If the current is moving out of the page, okay, out of the page, right? Okay, your thumb will be pointing out of the page. Your magnetic field will be this way. Do you remember about this? So if there is a current, it will produce a magnetic field around it. Okay, you use the right hand rule, your thumb pointing to the direction of the current, your finger will be the direction of the magnetic field. Okay, then the reverse of this, there's a slight change. When there is a magnetic field, you're able to produce a current. The only difference is the magnetic field must be changing. If the magnetic field don't change, there'll be no current. Why? Why do I say so? Like on Earth, there's always a lot of magnetic field of the Earth, right? Then why is there no current? Because the magnetic field does not change. So to produce current, the magnetic field must be changing. So when there's changing, then there will be current. Is that clear? So that's the only difference of the opposite. Okay, so this question, any problem? No problem. I will go to the next one. Okay, let's do this one. Question 37. Everybody try now. Okay, Ryan has a question for me. No rate of change in magnetic flux, no current induced. Yes, in between you need to actually write something. If there's no rate of change in the magnetic flux, there'll be no induced EMF. When there's no induced EMF, there'll be no induced current. Okay, good question, Ryan. Okay, Yu Ting, well done. Xiao Xing, well done. Bei Kuan, well done. Hao Rui, well done. Oscar, can you try again? Okay, when you're moving in and moving out, it should induce a different pole down here. Okay, Oscar, well done. Ryan, well done. Okay, so everybody understand this now? How many of you need me to explain? The correct answer is B, correct? Okay, how many of you need me to explain? If you need me to explain, give me a yes reaction. If you don't need me to explain, give me a no reaction. Ryan, you give me a cup, you want to treat me coffee. Okay, so nobody need me to explain. I will skip. Let's do the next MCQ question. Okay, do question number 39. This one. Okay, this question looks similar. Okay, what's the answer? This question looks very similar. What's the answer for this? Okay, all of you know already, right? The answer for this is B. Well done. Okay, let's move on. Let's do the next question. Okay, so I don't need to explain this. You all should know this question is a similar question. So can you see some question are similar? Okay, but this question is funny. This question a bit different. So this question a bit different from the previous one because there's this thing called light. Okay, so why the previous question there's no light, but for this question there is light. Okay, but what is described here got nothing to do with the light. Okay, the current actually will only deflect when the bar magnet moves. And when the bar magnet stop, then there'll be no more current. So this light has no impact on this current. It's the bar magnet that produce the current. Is that clear? So this light itself is just to distract you. Clear? Okay, let's do the next question. Okay. Electromagnetic induction can be demonstrated using a bar magnet, a coil of wire, a sensitive ammeter, and connecting wires. So in the space below, who can try? Who want to try? Who like to try? Anyone? Who can try? Who like to try? Anyone? Okay, who like to try? Everybody remove your reaction. Anybody like to try? Anyone? Hello? Okay, Pei Kwan, let's you try this question. Okay, so far so good. Okay, well done, Pei Kwan. Okay, 1 mark for this diagram. Okay, very, very good. You need to also, okay, never mind. Don't need to say anything else. Okay, so how does this apparatus is used to produce an induced current? How is this thing used to produce a current? Okay, beside Pei Kwan, who else can answer this question? Type it out in the chat. And then explain why a current is induced in this experiment. So this one just explain how to produce what's the thing you need to do to produce a current. Then you explain why is the current being produced. Okay, so can you all try this out? Okay, Yu Ting, well done. Hao Rui, well done. How about the rest of you? Can you give me the answer? Okay, Xiao Xing. Well done. Okay, let me share with you all the answer. So far, I see all of you are able to give the answer. Very good. So how to produce a current? Okay, what you can say is this. When the bar magnet is pushed towards, or you can put away. The coil of wire quickly. Okay, so basically that's the main point you want to tell me. Okay, push the magnet towards the coil or into the coil of wire quickly, or you pull the magnet away from the coil of wire quickly. Okay, that is the thing you need to explain. But okay, so not explain. This is what you need to state. The action that create the current. Then for part B, you need to explain why this action will produce a current. Okay, so let's say we talk about push into the magnet itself. Okay, so let me just write here. Part B. Okay, so the first part is stating your answer to part 2. So when you do this, what happened? What happened? There is a change in magnetic flux linkage between the bar magnet and the coil of wire. So there will be a change, there will be some change in the magnetic field or the magnetic flux in, linkage. Okay, so how does this change create an induced current? Okay, so as a result, okay, by Faraday law, okay, an induced EMF is produced in the coil and an induced current is therefore produced in the coil. Is that clear? Okay, Ryan's answer is very good. Ryan, can you share your answer with everybody? Ting, your one is okay as well. Well done. Xiao Xing, you can share answer to everybody as well. Ting, you also can share. I think your answer is okay. How about the rest of you? Bei Kwan, Hao Rei, and Oscar. Can you attempt part B and show it to me? Okay, you can also go and take a minute to read Ryan, Xiao Xing, and Ting's answer. Also very good. Ting, you send to me again. Oh yeah, now I send to everybody. Okay, so can I move on to the next question? Okay, so for this question, if all of you are clear Okay, and I expect to see Hao Rui, Bei Kuan, Oscar give me the answer for B as well. Can you please at least write out the answer and show me? Because that will at least help you remember. So can I see Hao Rui, okay, Bei Kuan and Oscar to give me your answer to part B before I move on? Okay, Bei Kuan, well done. So now waiting for Hao Rui and Oscar. Can you all give me the answer for part B? Okay, very good. Okay, very good, everyone. So at least you all can type it out. It will help you register in your inside your head a bit better. Okay, that's what I hope will happen. Okay, let's do the next question. Okay, I want you to remember this diagram. Okay, remember this diagram. Thread, aluminum ring, and bar magnet. Okay, then we do these two questions. Okay, so let me just draw. Okay, so can you all try this question now? 4 marks. Okay, so you all can just write the same answer that you all gave me just now for part B into number 1. So everybody, whatever answer you all gave me just now for part B, change a bit of things, then that's the correct answer, the same answer. Okay, Bei Kuan, well done. Hao Rui, well done for part 1. Okay, Yu Ting, your part 1 is correct. Well done. Okay, Oscar, your part one is correct. Very good. Okay, Yu Ting, your part two. Yu Ting, for part two, can you say the left side of the aluminum ring will become what pole? Okay, can you actually mention that? Improve your answer for part two. Okay, Ryan, your part one is correct. Well done. You now share with everybody. Okay, for part one, I will not mention. Can everybody share your part one answer? Okay, everybody share part answer. I will not type it out anymore. Okay, I'll do part two answer. So why does this aluminum ring move away? Okay, why does it move away? So as you move the magnet towards it, what happened? Okay, so by Lenz's law, the induced current causes a magnetic effect that opposes the change causing it. So in this case, a north pole is induced on the left side of the aluminum ring. Okay, to oppose the incoming north pole of the bar magnet. Clear? Okay, so you can also write down. And since light poles repel, the aluminum or the ring will move away from the magnet. Clear? Okay, so I want everybody to type out the answer for part two in your own words and show it to me, everyone. Okay, improve your answer if you have done so. If you have not written the answer, type out the answer and show it to me so that I know that you are okay with part two. Okay, Oscar. Well done. Oscar, can you talk about Lenz's law? Yeah. Then you make it seems like you know your stuff very well. Ryan, for 2 marks, I may not give you the 2 marks. Okay, well done, Oscar. Let's do the next question. Okay, everybody understand Lenz's law now? Okay, you all know Faraday Law of Electromagnetism. Now you all know the Lenz's law. Do you all need me to revise one more time? Well, I haven't given you all this yet. Later I'll give it to you all. Okay, so Faraday Law of Electromagnetic Induction is where the induced EMF is directly proportional to the rate of change of a magnetic flux. So when there's a rate of change of magnetic flux, there's a lot of change, the induced EMF will be greater. Okay, that's what Faraday Law of Electromagnetic Induction says. Okay, Lenz's law says that the direction of the induced EMF is always such that its magnetic effect opposes the motion or the change producing it. Clear so far? Okay, so I'm just revising this. Okay, so let's go back. Let's do the last question for part 1. Okay, let's look at this question. Okay, part A, we skip lah. This one, you all should know, right? Or you all want me to draw up for you all? Okay, something like this. Can? Okay, so part A, I give you all the answer already. Okay, now you all do part B. When the magnet rotates and EMF is induced in the coil. So now explain why an EMF is induced. Okay, so this question, same thing. It's the part B again. It's always the part B. So let me give you the answer. Due to a change in the magnetic flux linkage, okay, with the coils, and EMF is induced by Faraday's law of electromagnetic induction. Okay, so can we all say something like this? As it rotates, right, there will be a change in the magnetic flux linkage with the coil, and therefore EMF is induced due to the Faraday law of electromagnetic induction. So can everybody type something like this and show me? Okay, let's continue. Let's continue. Okay, suggest one reason why for using iron core in the AC generator. Okay, let me see this. No. Okay, why do we use iron core in this AC generator? You don't need an iron core, ma. So why do we put the iron core here? So what does the iron core do? Okay, Yu-Ting, well done. Okay, so there's a reason why I put iron core. Same thing, for example, if we want to produce an electromagnet, okay, we can produce an electromagnet without iron core. With just a solenoid, okay, with just a solenoid, okay, there'll be also you also create a magnetic field here. But if I were to add uh if I were to add an iron core inside the solenoid, okay, this magnetic field will be even stronger. Okay, why is that so? Okay, do you all know why? Let me give you a reason why. Okay, so the iron core, actually what the iron core does, okay, it helps to concentrate. Okay, so basically this iron core concentrate, allow the magnetic field line to go through it rather than just freely move around in the space. Okay, so this iron core allow the magnetic field line to go through it. Okay, it actually go through it and so on. Is that clear? Okay, so it actually allows it to go through it and therefore concentrate the magnetic field line. Okay, so it helps to concentrate, okay, the magnetic field line, which allows for better flux linkage with the coil. Is that clear? Okay, so basically, okay, it actually allows the magnetic field to concentrate inside here, moving inside this coil. Okay, without the iron core, the magnetic field will be actually around everywhere. Okay, it may not be concentrated. So with a core, there is a place for the magnetic field line to move. Okay, is that clear? There is a place for the magnetic field line to move, and therefore, it actually helps to concentrate the magnetic field lines for better flux linkage with the coil. Okay, can everybody type this out now and show it to me for part 2? Everyone. Okay, well done, Yu-Ting and Yi-Ting. Why Yu-Ting type 2 times? How are the rest of you? How are you? Well done. Okay, let's go to the next question. Okay, I want you to remember this. Okay, remember this. So this output terminal is connected to a resistor. Okay, I connect to a resistor. Okay, and maybe I connect to an ammeter. It shows a current. Okay, it shows a current. So the question is this. When the north pole is approaching P, y'all listen carefully, not be typing it out. When the north pole is approaching P, you see that there is arrow pointing down. Why is the current pointing down? Okay, 2-mark question. Okay, this is the part B that I asked you to write just now. Okay, same thing. By Lenz's law, what happened? Can you explain? As this north pole is moving towards coil P, why would the current be in this direction? So can all of you type it out now? Ryan, can you explain? 2 marks. 2 marks. Okay, what does Lenz's law actually explain? Okay, so Lenz's law states that what? States that the induced current flows in a direction to oppose the change that is causing it. Okay, what is the change here? The change here is the north pole is moving towards coil P. Okay, so what is the what is the opposition? When it's coming nearer to opposite, you need to repel. Okay, so this part here need to become north so that it can repel. Is that clear? Okay, so as it moves towards P, to oppose this motion, it need to repel. So it need to be north here. Okay? Here will need to be north. For this to be north, the induced current will be in this direction. Is that clear? Are you clear about this? So when the current in coil P is in the direction as shown, so applying right hand grip rule, we find that a north pole is being induced at the end of the coil nearest to the approaching north pole of the magnet. Is that clear? Okay, so this north pole is trying to repel. Okay, it's trying to repel the opposing north pole based on Lenz's law. Okay, if you're clear about this, give me a thumbs up. Okay, I don't need you all to write this because you write this 2-3 times already. But are you able to explain like this what Lenz's law is about with something which I did not explain clearly last week? If you are clear, give me thumbs up. If you are not clear, can you type it out and show it to me? Okay, my exit question will be to ask you all to explain Lenz's law to me. So I give you a clue. You all can go and prepare. What is Lenz's law? Okay. Hey, why got people go away? After I say this, how already disappeared? Okay, last question. Okay, very last question. If the maximum output of the EMF is 20 volt, okay, if the V is 20 volt, and the resistor has a resistance of 2.5 kilo ohm, what is the maximum power produced in the resistor? Okay, what is the maximum power? What is the maximum power? So can you actually calculate? Okay. If you all can get this answer, I'll let you go in. But I don't need you all to give me the Lenz's law. Okay. Give me the answer. What's the maximum power? If my output terminal, right, has a resistor here, and the voltage, okay, the voltage shows 20 volt. All right, Ryan, well done. You may go. So what's the formula you use? Power is equal to VI. Okay, but I only got V and R. Okay, I don't have I. So what do I do? Okay, Oscar, you may go. So can I convert I to equal to V over R. Then you get V square over R. So what's your answer? Once you do this, you should get the answer. Okay, Yu Ting, you may go. Okay, Pei Kuan, can you calculate the answer? What's the maximum power you can get from this? Pei Kuan, power is not in joule. In joule is energy. Okay, Qiao Xing, you may go. Pei Kuan, your answer now. Okay, so basically you will get 20 square over 2,500. You will get 0.16 watt. Okay, Pei Kuan, you may go as well. Thank you, everybody. Good night. See you all next week. Goodbye.